Okay, maybe let's get started. So welcome everyone to Friday morning. This is just an announcement for those watching on YouTube that the slides have been posted on the website. So reminder, you can find them there. And so we're happy to have Pavel Safronov telling us about geometric Langlands program for 3 minutes.
Thanks, and thanks for the invitation. So I want to talk about some work in progress joined with David Ben-Zvi, Sam Cunningham, and David Jardim. And the general idea is we're making an attempt to formulate geometric Langlands program for 3 manifolds, or some version of the geometric Langlands program for 3 manifolds. And so there are 2 ways to view this talk, from a mathematical perspective and from a physical perspective. So from the mathematical perspective, I'll be talking about some interesting Langlands duality kind of statements for 3 manifolds. So there will be various objects appearing related to 3 manifolds, like homology of the space of connections on the 3 manifold, Skein modules, and complexified instant Floer homology of 3 manifolds. And from a physical perspective, I'll be talking about a topological twist of the 4-dimensional n equals 4 super Mills theory, which is called the GL twist. And so I'll be talking about this topological twist on a 3 manifold. So I'll be talking about space of states in this topological field theory. And then I'll also be discussing S-duality of this topological theory. Okay. So I want to begin with a very basic example that will kind of suggest where to go in the next 3 slides. But this example is going to be completely elementary. So let's look at the category of local systems on the circle. If you think about the category of local systems on the circle, well, what does it mean? It means representations of the fundamental group. And the fundamental group of the circle is just Z. And so representations of the fundamental group are the same as modules of the group algebra. Well, the group algebra of Z is the same as Laurent polynomials in a single variable. And modules over CZZ inverse is the same as the category quasi-kernel sheaves on C star. Okay, so if you trace this equivalence, it gives you an equivalence between something completely topological, so local systems on some space, and something coherent or algebra geometric, which is quasi-kernel sheaves on C star. One way to think about this equivalence is that the left-hand side is actually the A model, or the category of boundary conditions in the A model into the cotangent bundle of S1. So if you think about the Rapp-Foucault category of the cotangent bundle of S1, that's the same as the category of local systems in S1. And the right-hand side is the category of boundary conditions in the B model into C star. So you can think about this equivalence as a basic example of mirror symmetry between the cotangent bundle of S1 and C star. Okay. Let's try to generalize this example a little bit. So what I'm going to do is I'm going to take, instead of a single S1, I'm going to take a bunch of copies of S1. And then a little bit more geometry. So let's say you have a closed Riemann surface sigma, and let's take some algebraic torus, so C star to the n, just H. I'll also be talking about the dual torus. You might just think that this is also C star to the n, but in some sense it has some dual properties. So one way to say this is that if you look at the character lattice of the original torus, it's equivalent to the co-character lattice of the dual torus. So that's this equivalence. And then you can generalize this first equivalence in the following way. You can look at a category of local systems on the moduli space of algebraic or complex H bundles on sigma. And this category is equivalent to the category quasi-coherent sheaves on the moduli space of flat H-check connections on sigma. So if you unpack what this means, moduli space of H bundles, well, this is, again, a bunch of copies of S1. Maybe you can think about H being just single C star. Then this is a Jacobian. So this is S1 to the power of 2G. And on the right, you have representations of the fundamental group of sigma into H-check. So this is, again, going to be a bunch of copies of C star. Right. So the point is that this bottom equivalence is a generalization of the top equivalence. And again, you can think of this bottom equivalence as a mirror symmetry between the A model into cotangent bundle of the moduli space of H bundles, and the B model into the moduli space of flat connections for the dual torus. So maybe let me quickly mention the appearance of the dual torus here. So if you just look at functionality, so here H is completely arbitrary torus, so you can think about functionality of spectral lattices. So the left-hand side is functorial in H. This is like local systems or like homology, so it's covariant in H, while the right-hand side is contravariant in H-check, because quasi-coherent sheaves naturally pull back. So if you have something contravariant in H-check, it's going to be covariant in H. So that's why there's this duality appearing on one of the sides. Okay. But this story so far is just the story about abelian groups, so some tori. Let's see if we can try to make sense of that in the non-abelian setting. So let's say you have a reductive group G. You can try to imagine that there's, again, the same kind of equivalence. So you look at the local systems on the moduli space of G bundles on sigma, and quasi-coherent sheaves on the moduli space of flat G-check connections in sigma. So here, G-check is what's called the Langlands dual group to G. In the case that this reductive group G is just a torus, so C star to the N, this Langlands dual group is just the dual torus. So it reduces to the case I was talking about before. If you're not familiar with Langlands dual groups, one thing to say is that, let me just give two examples. If you look at SLN, the dual group will be PGLN. And if you look at the odd orthogonal group, the dual group will be the even symplectic group. Maybe one more thing to say is that the fundamental group of G is exchanged with the center of the Langlands dual group, and vice versa for the center of the original group is exchanged with the fundamental group of the Langlands dual. Okay, so you can contemplate this kind of equivalence at the top, and you can see that it's actually not true. So even though it was true for the torus, this naive generalization for non-abelian group is not true. And you can imagine, or you might start getting worried when you start to write down this equivalence on in terms of some physical theories. If you think about the left-hand side, this is going to be the A model into the cotangent bundle of modular space of G bundles. But the cotangent bundle is non-compact. So there are different possibilities for what you might mean by the A model. More concretely, instead of the wrapped Foucault category, instead of a completely wrapped Foucault category, you can look at a partially wrapped Foucault category on the left-hand side. Something similar on the right-hand side, you're looking at the B model into the moduli space of flat connections. As opposed to the abelian case, this moduli space of flat connections is singular in the non-abelian case. So there are again various possibilities what you might mean by the B model on a singular space, such as the moduli space of flat connections. And the kind of So I will talk more about what kind of changes you need to make this equivalence true. But let me quickly say what you can do to the right-hand side to enlarge it or to change it. So here's a simple example of a B model on something singular. Let's take just a smooth variety with a potential, which has an isolated singularity at the origin. Well, the naive answer for the B model would be just the category quasi-coherent sheaves on that hypersurface, which is F inverse image of 0. But you can actually enlarge this category quasi-coherent sheaves to what's called the category of incoherent sheaves. So these were studied by Gatesgory, Frenkel, and many other people. So I will not define what I mean by that. You should just think that you allow more objects in that category. Well, if you have a larger category, you can just take the quotient and you can ask, what is the quotient? So incoherent sheaves by quasi-coherent sheaves. So what's the difference between them? It turns out that the difference is something familiar. It's the category of matrix factorizations of F. And so if this hypersurface is actually smooth, then the right-hand side will actually be 0. Okay, and in physics, this is closely related to what's called the Landau-Ginzburg-Calabi-Yau correspondence. So the right-hand side is what you would attach in the Landau-Ginzburg B model. Okay, so that's roughly the idea, is that we want to enlarge quasi-coherent sheaves to add more objects, for instance, incoherent sheaves. Okay, but before I say a fairly precise mathematical conjecture, I want to go back to physics and explain how these kind of equivalences arise in physics. Okay, and this is following the work of Kapus and Witten from 15 years ago. So you can look at the 4-dimensional maximally supersymmetric Yang-Mills theory. There are various interesting topological twists of that theory you can look at. For instance, there's the Waffe-Witten twist or some other twists. And they've considered what's called the GL twist. I will not tell you all the details. Let me just summarize the main points which will be relevant for this talk. So the idea is that there is some 4-dimensional TQ of T, what I call Z sub G, comma psi. So here G is again the reductive group G that I was talking about before. And psi is a parameter on CP1. Okay, so there's a family of topological field theories parameterized by the two-sphere. The 4-dimensional maximal supersymmetric Yang-Mills theory has an S-duality. And this S-duality gives you some equivalence of these topological field theories. And you can unpack what this means for this particular topological field theories. And you see that the theory for the group G, so the 4-dimensional TKFT for the group G and parameter psi should be equivalent to the theory for the Langlands dual group, G check, and parameter -1 over psi. Okay, so this will be very important in the future. And here is, this is exactly how you see Langlands duality appearing. So there's a G on the left-hand side, and there's a Langlands side. There are some special parameters where the theory is a little bit easier to describe. For instance, you can take psi to be 0 or psi to be infinity. And as you see, this as duality exchanges these 2 points. So I can discuss those 2 points as special points. All right, so first of all, let's look at the case when psi is 0. So you have this 4-dimensional TK of t for psi equals to 0. You can compactify this 4-dimensional TK of t on the Riemann surface sigma, and then you get a 2-dimensional TK of t. And then you can ask, what is that 2-dimensional TK of t? Well, what Kappas and Whitney have shown is that this 2-dimensional TK of t is the A model into the Hitchin moduli space, which is the moduli space. So there are a few ways to think about this. One way to think about this is that it's the moduli space of Higgs bundles on the Riemann surface sigma. Another way to write this is exactly the cotangent bundle of the moduli space of G bundles of sigma. And when I say the A model, I have to specify which symplectic structure I'm talking about, because this Hitchin moduli space is actually a hyperkähler, so there's loads of symplectic structures. The symplectic structure I'm talking about is the natural symplectic structure on a cotangent bundle. In terms of the hyperkähler structure, it's the symplectic structure called omega k. Okay, so this is the first case when psi is equal to 0. And another interesting special point is psi equals to infinity. So again, you have some 4-dimensional TK of t corresponding to psi equals to infinity. And you can repeat the previous process. So you can compactify this theory on sigma and get some 2-dimensional TK of t. And then you can see that this 2-dimensional TK of t is actually the B model also into the Hitchin moduli space. Let me just repeat that the Hitchin moduli space is a hyperkähler manifold. So again, to specify the B model, I have to tell you which complex structure I'm talking about. In this case, the complex structure is what's called J. In this complex structure, the Hitchin moduli space looks like the moduli space of flat connections. And so this equivalence of this, the theory at psi equals to 0 compactified on sigma, and the theory for G check at psi equals to infinity compactified on sigma looks exactly like what we wanted. On the left-hand side, we get the A model into the cotangent bundle of moduli space of G bundles. And on the right-hand side, you have the B model into the moduli space of flat G-check connections. And so this is what I was trying to get at here, which was not quite true. But physically, it indeed exchanges the A and the B model. So it's a mirror symmetry. Okay. Now this is this S duality is, as I said, it's an equivalence of 4-dimensional TK of T's. So there's a lot more structure you can see besides just this equivalence of categories. And there are structures of different categorical levels. So there are some structures of a 3-categorical nature, of a 2-categorical nature, 1-categorical nature, and so on. So one thing you can extract out of a 4-dimensional TK of T is the 2-category of surface operators. This 2-category of surface operators in terms of the functorial approach to TFTs, you can think of this as the compactification of this 4-dimensional TFT on the circle. And then if you just count the category number, this should be a 2 category. And so if you think about this equivalence of the 2 categories of surface operators in these 4-dimensional TFTs, you arrive at what's called the local geometric Langlands correspondence. So the local geometric Langlands correspondence is an equivalence of some 2 categories. Something I've already talked about is the case of the surface. If you compactify in the surface, you get an equivalence of 1 categories. And this is the global geometric Langlands correspondence. What I want to talk about now in this talk is what's going on for 3 manifolds. So if you compactify in 3 manifolds, you get 1-dimensional TFTs, so you get an equivalence of Hilbert spaces. Okay, so I want to say a few words about what these Hilbert spaces are. Okay, let me pause for some questions if there are any.
So I have just a naive one, but you made a point of specializing to the special points on the Langlands case and leaving the finite psi in your new vector space case. So it's the equivalence that you're going to be talking about, like for every finite psi, or just for the special points?
So there are things of different nature happening at cycles to 0 or cycles to infinity and for generic psi. So we'll actually be talking about the 2 cases being cycles to infinity or 0 and generic case. There are special points like psi is rational where sort of 2 things, both complications arise, but it will be useful to separate the 2. So the stories are kind of a different nature at cycles to 0 and psi being generic. Okay. All right, so now let me go back to some mathematics. So I promised to formulate a more precise version of the equivalence that I was writing here. So the naive attempt to formulate the global geometric Langlands was to say you have the category of local systems on the moduli space of G bundles, and this category is equivalent to the category of cosigner sheaves on the moduli space of flat Dirac connections. So this was true in the abelian case, but it turns out to be non-true in the non-abelian case. And the correct conjecture was proposed by Ben-Zvi and Nadler. And what they've done is that they've enlarged the category on the left-hand side. So instead of looking at local systems, you look at more general kind of sheaves. These sheaves on the left-hand side are required to have a fixed singular support. And whatever this means, it just means this category of sheaves contains the category of local systems. So it's a certain enlargement. Okay. On the right-hand side, there's also an enlargement happening from the naive version. Instead of the category of cosigner sheaves on the singular space of local systems on sigma, you look at this category of incoherent sheaves, and again, you fix the notion of singular support. So the right-hand side might be more familiar to some of you because it has previously appeared in the works of Henrique and Gaisgori when they were defining a precise version of what's called the Jardim, Germanic Langlands correspondence. So this is the version where on the left-hand side, instead of talking about sheaves or local systems, you talk about D modules, or if you like, vector bundles with a flat connection. Okay, so I will not say much about what these singular support conditions are. For symplectic geometers, the left-hand side is a partially wrapped Fukaya category with a cotangent bundle. So there is a, if you like, there's a stop, or there's a fixed Legendrian in the cotangent bundle of Ben-Zvi. And you can look at this partially wrapped Fukaya category, which is going to be this category of sheaves with a fixed singular support. And on the right-hand side, again, this is some version of the B model, something that appears when you talk about B model into singular spaces. Okay. So let me try to say something a bit more precise. So slightly refine this conjecture. So again, what happened is that you have these two categories, this local systems and quasi-coherent sheaves, and you have two enlargements. But it turns out that this conjectural equivalence, it's not even supposed to match those nice subcategories, so local systems and quasi-coherent sheaves. But let me explain what's going on with these categories, with these easy subcategories. Okay, so besides just the inclusion of local systems into all sheaves, there's also an adjoint functor. So given a sheaf, you can create a local system out of that. So you have this functor. In terms of Fukaya category, there's a, I guess it's called the acceleration functor from the partially wrapped Fukaya category to the fully wrapped Fukaya category. You can take its kernel, and this kernel is what I will call the tempered part of the category of sheaves. And the idea is that all three categories on the first line are supposed to be values of some 4-dimensional TK of T on sigma. So there is this kind of a Betty TK of T. And this gives you the middle column. It has a tempered part, and then you can take the quotient by the tempered part and you get this naive category of local systems. So sort of completely topological part of Ben-Zvi. If you go to the B model, okay, again, you have this naive part, the category of quasi-coherent sheaves. It includes in the category of incoherent sheaves, so you can take the quotient. And now these naive parts don't match, but instead they kind of match with the complements. So the category of local systems matches with the complement to the category of quasi-coherent sheaves. And vice versa, the category, this tempered part of the category of sheaves on Ben-Zvi matches with quasi-coherent sheaves on the category, on the modular space of flat G-check connections. Okay, so the idea is that there's supposed to be, in this case, there's 6 4-dimensional TKFTs. There's the tempered part at cycles to 0, which gives you sheaves. And then there's a version which gives you quasi-coherent sheaves, and those two match. Then there's the fully Betty part, which gives you the original conjecture. And then there's kind of a topological part, which gives you local systems of Ben-Zvi and something on the B model part.
Sorry, Pavel. So is the bottom line, the first map, is it some sort of like Drinfeld-Sokolov reduction?
You're talking about this? Or which part? Or did you say the bottom horizontal map, or? Reimundo?
Oh, am I mute? Oh, thanks. So yeah, the first bottom horizontal map.
Yeah. So yeah. Again, there's this enlargement of coherent sheaves into incoherent sheaves. One way to think about this is that if you look at compact objects in these categories, on the left you get perfect complexes, and on the right you have coherent complexes. And on a let's say on an LCI scheme, perfect complexes embed into coherent complexes. So it's a naive inclusion. There's nothing complicated going on really. Okay. All right. So this is a mathematical conjecture, but let me explain how this relates to the sort of 4D TKFT described by Bursztyn and Witten. The idea is that, well, you have this complicated physical 4-dimensional TKFT, and it's very difficult to describe it completely. And I will not try to describe the theory completely, but I will just take certain pieces of the TKFT. And when I say certain pieces, I'm going to look at some local operators or some line operators generated by some boundary conditions. Okay, so let me describe for you some boundary conditions to this Bursztyn-Witten TKFT. Unfortunately, I haven't figured out good names for these boundary conditions, so we'll just come up with some strange names. So let me first describe the case cycles to zero, the two boundary conditions in that case. So one of them is what I call the zero section. If you compactify the cycles to zero theory on sigma, you get the A model into the Hitchin moduli space. And so this boundary condition will be given by some A brane. This A brane, in this case, is just the zero section of the cotangent bundle. The other object, the other boundary condition, is what I will call the automorphic Whittaker sheaf. In terms of physics, you can think, so in terms of string theory, you can realize n equals 4 super mills as the Ward volume theory on D3 branes. And then you can look at D3 branes ending on D5 branes. So this is what's called a non-pole boundary condition. And in terms of the compactified sigma model, this corresponds to the brane of operators. Okay, so these are two boundary conditions at cycles to zero. And then there are also two boundary conditions at cycles to infinity. So one of them is the Sparkle-Whittaker sheaf. Again, if you compactify it to a B model description, there's some rather interesting B brane, which is supported just at the trivial local system in the modular space of flat G-check connections. So these two are exchanged under Langlands duality, and these two are exchanged as well. Yeah, so the last one is what's called the NS5 brane boundary condition. In terms of the B model, this corresponds to just the structure sheaf of the Hitchin moduli space. Okay, and if you have boundary conditions in a 4-dimensional TKFT, you can look at the categories of line operators on these boundary conditions. So this gives you some braid monoidal categories. And you can try to estimate what those are. For the first pair, so the zero section and the Sparkle-Whittaker sheaf, the braid monoidal categories you get are the following. So for the A model, you get local systems on the classifying stack, BG. And for the spectral Whittaker sheaf, you get some other description. Maybe I'll not say much about it. And then there's another equivalence of braid-monoidal categories of line operators on the NS5 brane boundary condition and the D5 brane boundary condition. So this one is the D5 brane. This one is an NS5 brane boundary condition. Both equivalences of braid-monoidal categories are actually mathematical statements. They're true mathematical statements. Okay. Now, as I said, you have these boundary conditions, and you can look at pieces of the TKFT, of the four-dimensional TKFT, seen by these boundary conditions. And the claim is that the piece that's seen by this NS5 brane boundary condition, or the D5 brane in the dual description, is exactly the tempered part of the Betti TKFT. So this is tempered.
What does tempered mean?
So one way to define it on the B model side is it's the piece where we just see quasi-coherent sheaves on the modular space of G-check connections. It has a slightly more complicated description on the A side. So there's an abstract definition in terms of this kernel of the restriction map to local systems. And then if you look at the other two boundary conditions, so again, if you look at the TKFTs seen by these boundary conditions, they will again match up. And these are the TKFTs corresponding on the A model side to just local systems on the modular space of G bundles. Okay. So the idea is that this Betti geometric Langlands TKFT, it's the piece of this GL twisted for the TKFT, which is seen by only these two boundary conditions. But instead of just looking at the two boundary conditions, you can look at the one boundary condition, and then you get one or the other piece of the TKFT. Okay. So far, what I've explained is what's going on for Riemann surfaces. And the idea is that you can try to use these ideas to contemplate the version of the geometric Langlands program for three manifolds. Again, so far, I'm just describing the case psi equals to 0, psi equals to infinity. So let me sketch how this looks like. So again, let me begin with the true and easy fact in the abelian case. So if you look at the moduli space of bundles with a connection, and let's say I'm again looking at the case of the algebraic torus, so C star to the n, I can look at the homology of this moduli space. And you can match the homology of this moduli space with the algebra of functions on the moduli space of flat H-check local systems on M. So again, whenever I'm talking about flat, whenever I'm talking about local systems, it just means representations of the fundamental group. Mod conjugation. So here on the right-hand side, I'm looking at, so the right-hand side is some very singular object, and I'm looking at derived algebra functions. So I'm also including, if you like, fermions and so on. Okay. And the top equivalence should be compared to what's going on in 2 dimensions. So in 2 dimensions, the analogous statement is that local systems on, let me just say moduli space of H bundles is the same as quasi-coherent sheaves on the moduli space of H check connections on sigma. Right. So this is what's happening for the case the group is abelian. In the case of non-abelian group, you again imagine we expect that there's a similar kind of filtration. There's a tempered part, which is easy on the B model side and complicated on the A model side. And there's the complement to that, which is easy on the A model side and complicated on the B model side. So the easy part on the A model side is just homology of the space of connections. The easy part on the B model side is the derived algebra of functions on the moduli space of G-check local systems. But whenever you're dealing with these singular objects, there's an enhancement of the derived algebra of functions you can consider. If you like, this is some kind of distributions you might consider on this singular object. They're not distributions along kind of ordinary directions, but they're distributions along even directions, but which are not in cohomological degree 0. So the idea is that you can again imagine this enhancement on the B model side, on the A model side, and the two should match. Okay. So for the B model side, you can define it rather easily in this particular case of local systems because it has a nice presentation. And there's a more general theory that's being developed by Dario Beraldo. Okay. You can also, as a check, you can see what's going on for the 3-sphere, and you get a true statement there. Okay. So far, I've been talking about the case cycles to 0 or cycles to infinity. Now let me move to a completely different regime, which is the case where psi is generic, meaning irrational. In some senses, this case is actually simpler. And let me explain what this means. So one expectation is that when you deform from cycles to infinity to generic psi, this piece, so there is the left-hand side, the column on the left is the tempered part, and the middle column is kind of the whole TKFT. And then there is the difference, which is the right column. So the expectation is that for generic psi, this right column is just 0. So actually everything is tempered. So this is the first simplification. So you don't need to deal with this difference between functions and distributions. Another thing to mention is that if you deform away from cycles to infinity, what you get is, so first of all, cycles to infinity, as I said, what you get is derived algebra of functions on the moduli space of G local systems. This algebra of functions has a natural Batalin-Mikhailovsky anti-bracket, just because this moduli space of flat connections on the 3-manifold is the critical locus of the transimus functional, and functions on the critical locus of any functional has a natural Batalin-Mikhailovsky anti-bracket. And so then you can talk about Batalin-Mikhailovsky quantization of this space. And there's a model for what this BV quantization is, which was introduced by Bussy Joyce and other people. Basically, whenever you have what's called a -1 shifted symplectic stack together with and orientation data. So I will not say what this means, but local systems on the 3 manifold is an example of such. Then there's a natural perverse sheaf that you can construct. And the homology of this perverse sheaf is expected to be a model for this BV quantization. In this particular case, if you look at the homology of this perverse sheaf for the case of the modular space of flat connections, this was considered by Abozit and Manolescu, and this is precisely what they called the complexified instant Floer homology. So let me explain the words. Maybe you're familiar with the usual instant Floer homology. So the usual instant Floer homology is supposed to be the Morse homology of the transimus functional on the modular space of connections on the 3 manifold, let's say SE2 connections on the 3 manifold. And this is a similar version where you look at complex transimus functional the modular space of complex, so SL2C connections. And so the expectation is that this full TQFT that I'm talking about for generic psi is just this complexified instant Floer homology. Okay. So Emily, I think I started a little bit late. How much time do I have?
You have about 4 minutes.
Great. Right. So now if you combine this with S duality, you naturally come to this conjecture that this complexified instant Floer homology for G and for G check are isomorphic. Okay, so this is a rather big conjecture. This complexified instant Floer homology was just introduced very recently, and there are not a lot of computations. Something you can check is that if the fundamental group is finite, this claim is true. So if the fundamental group is finite, everything is just reduced to the maximal torus, and then there's some easy statement about maximal tori. Okay, so you can ask if you can make this conjecture even more concrete. So this already looks much simpler than what I was talking about before. It's equals to 0, equals to infinity. But let's try to make it even simpler. And to make it even simpler, I'll remind you the notion of a Skein module. So for physicists, the Skein module, the idea of the Skein module is you look at all possible operators in transimus theory, or possibly analytically continuous transimus theory, which are generated by Wilson lines. So this means, more precisely, you draw all possible Wilson lines in the 3 manifold, and you impose the relations that they satisfy. So for instance, in the SL2 case, if you have a crossing like this, you can resolve it in 2 ways, up to some factors of Q. So there's a precise definition in the SL2 case here. So one fact, so the Skein modules have been introduced by Przewalski and Turaev 30 years ago. One fact that was proven recently by Cunningham, Jordan, and myself is that for generic Q, and Q, generic Q just means generic psi, which was the parameter I was talking about before, the Skein module is actually a finite dimensional space. So it's some interesting finite dimensional vector space. And these dimensions of Skein modules, it's something quite interesting, and people have been computing them for many years, and there were some interesting computations in the last few years. So how does this relate to the story I was talking about before? So the claim is that, so this is what we prove in some Cunningham, is that if you look at the 0th homology, the 0th complexified instant Floer homology of the 3 manifold, then this is exactly the Skein module. So if you like, the complexified instant Floer homology is actually a derived enhancement of the Skein module. Okay, so if you combine this with the previous conjecture, then you arrive at this conjecture that the Skein module for G should be isomorphic to the Skein module for the Langlands dual group for generic Q. You can check that this again true for G a torus, so C star to the N. And this is a rather easy statement, and it goes back to some old work or sheet scheme. A more natural statement is that this is actually true for SL2 and the 3 manifold being surface cross S1. Again, while this statement maybe looks sort of maybe obvious, it does contain some natural information. For instance, it implies that the cohomology of the character varieties can be computed in terms of the Skein module. So as an example, there's a embedding of the middle dimensional cohomology of the twisted character variety for SL2 into the Skein module for sigma cross S1. Okay, and I will stop here. Yeah, thanks.
Are there any questions?
Well, at the very end, what was meant by twisted Skein module? Or, sorry, twisted character variety.
Twisted character variety just means that there are a few ways to formulate this. One way to say is that instead of saying, let's just look at for the 2 torus. For the 2 torus, you can say the usual character variety means pair of elements whose group commutator is 1.
Yes.
And instead of saying that, you can say it's -1.
Okay. So it's like for SO3 having W2 non-zero.
Exactly.
Right, okay.
It's what makes this character variety actually smooth.
Okay.
Ezra gets another question.
Yeah, hi. Do you mind paging back a slide or two? I think maybe 1 slide. No, 2 slides. No, 3. There. So, so I've got 2 questions. The first is, so what, technically speaking, which model of the derived functions on this derived stack, which is an actual differential graded commutative algebra, do you use, or are you actually studying homotopy Bertalan-Vilkovisky structures? That was my first question, and maybe more less technical question about the derived sections of the perverse sheaf. Can I think of that as related to Kudavedian's module, the half densities on a Bertalan-Vilkovisky manifold?
Let me maybe answer the second question. I don't think I can say anything technical about the first question. For the second question, the idea is that this right-hand side, it's not just sections of the half densities, but it's the sections of the half densities equipped with the BV Laplacian.
Yeah, well, that's what I mean. That's what, yeah, of course, it's a complex. So is that the role, in other words, of the construction of Bussy et al? I never understood that. I see.
So the Bussy work, Bussy, Joyce, and others, they work in the topological setting. So there's no Bertalan-Vilkovisky quantization at all.
Oh, I see. Okay, right. I know
this is more of a suggestion.
Right. Half forms and not half densities. So there's an extra choice of orientation in sense of Kontsevich-Sobelman.
No, I would say in the complex setting, there's no difference between the 2 things.
Okay.
The orientation date is precisely the choice of that square root.
Okay, but I'm going to return to my first question because you're listed as one of the authors. So you must have something technical to say about your own theorem. I mean, when you say it's a Bertalan-Vilkovisky, oh, so you don't have a product. You only have the anti-bracket. Is that the situation?
Maybe I can explain it to you at some other time.
Okay.
Like what precise statement is. But this work should appear in a few weeks or so, or in a month, hopefully.
Great.
I think the next question was from Greg Moore.
Yes, I have just a very naive question. So I've always been rather puzzled by the fact that in the with the Donaldson twist of n equals 2 super Yang-Mills, although it was the first topological field theory, it's not really a topological field theory because the Hilbert space is instanton Floer homology, which is troublesome to define on all three manifolds. So what I'm understanding you to say is you're telling us what the Hilbert space is on all three manifolds, at least when psi is generic. When psi was special, you seem to have several candidates, which puzzles me. But is that a way to think about it? And do you expect that will actually fit into an official extended topological quantum field theory?
Yeah, it's a good question. So what's going on here is that what is expected is that there's a theory that is well defined on three manifolds, two manifolds, 1 and 0 manifolds. It does not give you a well-defined theory in the original functorial formulation on 3 and 4 manifolds. So a priori, this vector space on 3 manifolds could be infinite dimensional. So there was some theorem that I mentioned that these are fine dimensional, but
so it won't be fully dualizable. So these are infinite dimensional spaces.
They happen to be fine dimensional, but for a complicated reason. But
so finite dimensional, but
correct. The object you attach to the point is not fully dualizable. It's 3 dualizable, but not 4 dualizable. So this theorem is a somewhat unexpected theorem, let's say.
Okay, let's have one more question from Aaron, and then remaining discussion should be maybe deferred till lunch.
Hi. Can you hear me?
Yes.
Yeah.
Okay. Yeah. So in the two-dimensional story, there is this interesting argument you said that you can recover those interesting bonoidal categories, like the Whittaker sheaves and the Grossmanian. Is there also some story in the three-dimensional one where you get some sort of algebra structure, or is the algebra structure that you get on those spaces just from the homology?
Right. So this is actually not. I wouldn't say it's a two-dimensional story. I would say it's the story about the four-dimensional TKFTs. So here I'm just talking about the categories for line operators, which are Braid-Mannerl categories, and then given a Braid-Mannerl category, you can construct a four-dimensional TKFT or some piece of that. And so what I'm writing at the bottom is what are those four-dimensional TKFTs on surfaces, and what I was proposing next is what they should attach to 3 manifolds. But it's still a four-dimensional TKFT, really.
Okay.
All right, I think we're out of time. I'm sorry, I see that Edwin has another question. Hopefully Pavel can answer that in the lunch break. So I think we should take a 5-minute break and then resume again at 37 minutes past whatever hour it is where you live. And let's thank Pavel again.